Hello everyone, my name is Chen Xi. In this video, our group will talk about our final project, Image Dataset Compressor for Machine Learning using Principal Component Analysis. We will first give an overview of our project and discuss the algorithm we use and its optimizations. The results will be discussed and we will present a short demo. So PCA is a dimension reduction algorithm by finding the orthogonal basis, which maximizing the covariance of the input data. Our objective of this project is to accelerate PCA with FPGA, and the baseline design is a C code running on ARM core of the Z board, and the alternative design is the FPGA-based accelerator on Z board cooperated with software. So this image shows the PCA image compression flow. We first use the MNIST dataset, and the first step is to reshape the original dataset and normalize it to zero mean. Then we calculate its covariance matrix, and we perform the singular value decomposition, which is SVD, to find the orthogonal singular value matrix and its corresponding singular eigenvector matrix. By finding the first K principal components, we obtain an orthogonal basis transfer matrix. And finally, we get the compressed result by backprojecting the transfer matrix to our normalized input. Noted that the SVD part is the most computationally intensive part in our process, and our main focus is to optimize this part. Also noted that since our covariance matrix is a squared matrix, we're actually performing eigen decomposition, which is a special case of SVD. In next part, Kejia will talk about the algorithm we used for SVD and our optimizations.
So let's begin with the simplest SVD method called two-sided block Jacobi method. The reason why it's called the two-sided because we need to generate two rotational matrices, Jn and Kn, from the input matrix An, where Kn and Jn compose of two rotational angle C and S. By accumulating those multiplications, we can get A, U, and V. And when n, the iteration time, proceed to the positive infinite, we can get the result of the SVD, sigma, U, and V. But in practice, we set n equals to 6. So, what about the block method? It is very easy to find the 2 times 2 equivalent about the SVD method by read 4 old values out from the matrix and calculate and write back the new values to the An plus 1 bar. But that will also cause some issues when the dependencies. That is inevitable. For example, let's look at this pseudocode. N is the iteration number, and I and J is the diagonal indices. When we want to execute the whole 2 times 2 SVDs, we need to execute every combination about I and J. And we need to fix the value of I's, and then change the value of J's, and then execute the 2 times 2 SVDs. But that will have some dependency issues, because when you update the rows and columns about the A's, you need to update all the rows and columns associated with I and J's. So there must have some overlap parts. So that will cause some dependency issues. So how do we fix that? We fix that by the round-robin scheduling. So let's introduce some notations about the rectangles. 0 and 1 represent the value of I and J's. For example, if we have a 3 by 3 matrix, we'll have 3 combinations about these rectangles, and each rectangle represents an iterator about the SVD, 2 by 2 SVD. So after execution this SVD, we will fix the value of 0, and then rotate and sweep all the rest of these values to get the new combinations. This animation shows. So now we need to execute the SVD again, and until every combination will be executed, and we will finish a sweep of this SVD. By this method, we can achieve a higher parallelism and a higher speed up.
Hi, this is Yujie, and here is the structure for our hardware design. And we can see that the input for our PCA accelerator is 200 MNIST image, and the output is two matrix. The first one is a compressed image, and the second one is ordered principal component. Each pixel for these two matrices is represented by one float, which is 32 bits. And here is our result for our code sim. The problem is that even if we use the downsampled version, which is 4x4 dataset, we still run out of resource. But this code sim did verify the correctness of our algorithm. And we can see that our alternative design optimized our code sim latency comparing to the baseline for SVD, and also another alternative design that provided by Xilinx. So for the next section, Yutong will tell us how do we use hardware and software co-work to solve this problem.
This is our system architecture diagram of hardware and software co-design. The normalization, the sort and ranking are running completely on the host with software. The covariance matrix calculation, the SVD, and the back projection are helped with FPGA. We have a 2x2 SVD unit to calculate the two rotation matrices. It is running in a pipelining way within each round-robin iteration so that we can reduce the latency. The update of the SUV matrices are also pipelined. The interface between the host and the FPGA is 2 float 32 AP50. Here is our testing result. We can find that the testing speed up for 4x4 dataset is the highest, while the speed up for 10x10 and 28x28 are relatively slow. We concluded that this is due to the limitation of our interface, which is just 2 float 32 FIFOs, and we should be able to achieve better performance if we have an interface with higher bandwidth. Here is the end of our presentation, and we also have a demo.
So now I will give a very brief demo of our project. So now I'm in ECE Linux server, and first we want to run a very simple CSIM on the original MNIST dataset with 28 by 28 and 100 images, and we want to calculate the first 10 principal components. So now we got our results, and our results is saved in the data folder. So what we care is the final results, which represents our compressed image data, and this transfer matrix, which we would use to recover our images. So now I copied these two data to my local computer and used this Python script to show the original dataset and the final recovered images. So let's load the original MNIST dataset, and so here this is the original MNIST dataset, and we only show these first 10 images. This is our recovered images. So notice that our compression is a loss compression, and we only take the first 10 principal components of the original dataset. So we think this result is acceptable. Now we're on the Z-board FPGA, and here we used the downsampled MNIST dataset with size 4x4. And now we run our software and hardware co-design version on the FPGA. And here our result is compared with the golden reference generated by Python PyTorch package. And we can see here our result is correct. Thank you for listening.